One of the distributions that we work with most frequently is called the normal distribution. And even if you haven't heard that name before, you've probably seen it. It's our familiar bell curve. And the formula for this graph is based on the mean for my random variable and the standard deviation. Note that we're using sigma, the standard deviation, and not sigma squared, the variance. The distribution has its midpoint or most likely value at the peak of the curve at whatever the mean value is, and I can change the formula for the curve by shifting it from one mean value to a new mean value without changing the shape of the curve, only its location. So these two curves are the same standard deviation, but just have different means. If I change the standard deviation but leave the mean the same, I get a curve that is flatter and more spread out, but has the same midpoint. This flat, spread out curve represents one that has a high value of sigma, or high standard deviation, a lot of variation in the possible values, a wide range over which they fall. Now there's so many different combinations that we can come up with for different values of mu and sigma that we standardize in order to handle them efficiently. We standardize these into what we call a standard normal distribution. And that standard normal distribution has a mean value of 0 and a standard deviation of 1. And we use the letter z to represent a random variable that has a standard normal distribution with a mean of 0 and a standard deviation of 1. Now this is very useful if we happen to have these values, but we'll almost never find them in practice. We'll find other values for our mean and our standard deviation. And so what we do is a transformation to take whatever random variable we have, as long as it's normally distributed, and convert it into a standard normal by taking that random variable x minus the mean value divided by the standard deviation. Now to see how we would apply this, let's say we've got a distribution that has a mean value of 10 and a standard deviation of 2. For that random variable with those parameters, we want to find the probability that it has a value that's less than 7.5. So if we look on the curve, if we plot this curve, 10 is at our midpoint, 7.5 is going to be somewhere down here. So we're asking what's the probability that we fall in this range down here near the bottom of the curve. To find this probability, we apply the transformation formula to get a standard normal random variable. X is 7.5 minus the mean divided by the standard deviation, values over here. And we find that we need to know what the probability is that a standard normal random variable will fall below 1.25. Oh, sorry, negative 1.25. So we have 7.5 minus 10. Now to find this, the back of the textbook and many other sources have tables for the standard normal distribution. For many values of z, whatever value of z we want to look at here along the bottom, it gives us the value for this area, the shaded portion that is below. This is our cumulative distribution table. The table is divided into two pieces. First we look on the left side to find negative 1.2. Gives us the first decimal place, and then we look across the top to find 0.05. Okay? Where those values intersect, 1.1056, that's our probability for z being less than negative 1.25 and for x being less than 7.5. Gives us the probability for an outcome that is less than whatever cutoff we used. Now the tables can work in the opposite direction as well. if we know a probability, we can find what cutoff is associated with that. So if we want to find a value below which 90% of our values fall, so now we're on this curve, we're up at this upper end, and we want to say what's the probability that 90% of our outcomes are below this limit X, this cutoff. How high do we have to go in order to include 90% of the outcomes? We come back to our standard normal table, which can tell us what value of Z corresponds to that 90% cutoff. If we look at the values, we find that the closest number, and if we're only looking at 3 decimal places, it's going to round to 0.9, is 0.89727, and that comes from Z equals 1.2, and then the second decimal place is 8. So we find out that this corresponds to a value of Z equals 1.28. If we apply our transformation again, and this time solving for X, we find that X is equal to Z times sigma plus mu, and that's equal to 1.28 times 2 plus 10, which is equal to 12.56. So for this situation where I've got this mean and this standard deviation, mean is 10, standard deviation is 2, 90% of the time I'll have an outcome that is below 12.56. And again, you can see that's somewhere up on the upper end of the range where my mean is 10, that cutoff is up here at 12.56.